What if two visitors from the deep, unbound by any star, happen to cross the same patch of our sky at once? You see, somewhere out there in the cold gulf beyond Neptune, two interstellar travelers, 3I, Atlas and C 2025, V1 Borisov seem, at least from our line of sight, to align. It's almost poetic, isn't it? The first, a silent wanderer already leaving the sun behind. The second, newly discovered, moving upward through the plane of our solar system, its faint glow barely brushing the background of Virgo. Are they truly passing one another in space? Or is this just a trick of perspective, a two-dimensional illusion drawn by geometry and light? Perhaps the cosmos itself is teasing us, showing two ships that look close enough to touch, but are in truth separated by unthinkable distance. And yet, that image of them, hanging together in the same frame, stirs something ancient in us, the urge to measure, to understand, to ask what lies between. Before we go on, I'd like to ask you to subscribe to the channel and leave a like. My aim here is simple, to help you drift off to sleep while exploring the wonders of science. Where are you on the map? Let me know where you are in the world and what time it is in the comments. It's always fascinating to see who's joining us from all around the world. So let's continue. It begins, well, as all stories of discovery do, with a flicker of light on a telescope sensor, a pattern noticed, a signal pulled out of noise. Early in November, astronomers around the world reported something subtle, yet unmistakable, a faint smudge that moved differently from the stars. At first, it was known only by a code, a sterile sequence of letters and numbers, GB 0000810. But soon, as the orbit was refined, the object earned a name that carried a quiet weight, C 2025, V1 Borisov. The name itself felt like an echo of a story we'd heard before, another Borisov, another interstellar visitor. Only, this time, it appeared on a path that, when drawn on our celestial maps, lay between Earth and another wanderer already known to science, the enigmatic 3I Atlas. Now, that phrase, between Earth and Atlas, sounds simple enough, doesn't it? It paints a picture of cosmic alignment, a straight line connecting 3 points across the dark. But you see, astronomy often plays tricks with our intuition. The sky is not a flat canvas, it's a vast three-dimensional sea of distances. What seems close together to our eyes might, in truth, be separated by hundreds of millions of kilometers. So when we say that Borisov lies between Earth and Atlas, we must ask, between, in what sense? On the projection of the sky, yes, the direction aligns. But in the real geometry of space, the story might be quite different. Still, that apparent alignment captured attention. The timing felt uncanny. 3I Atlas, a confirmed interstellar object on a hyperbolic trajectory, had just passed, its closest point to the Sun, its perihelion, and was beginning to drift outward, fading yet still strangely bright. Observations suggested its brightness exceeded expectations, roughly 1.5 magnitudes brighter than predicted. That means, by the logarithmic scale astronomers use, almost 4 times as luminous as the models anticipated. Yet despite that brilliance, Atlas showed little of the drama we associate with comets, no obvious tail, just a faint coma, a whisper of activity around a nucleus that seemed reluctant to shed. Meanwhile, C 2025 V1, Borisov, this new arrival, was approaching its own perihelion, expected around mid-November. Its light hovered in the range of magnitude 12 to 14, barely visible to amateur telescopes under a dark sky, but clearly there. Some images showed a coma, soft and grey, but most found no clear tail. 2 independent reports mentioned a possible faint streak, but the estimates of its length varied wildly. That's not unusual. When dealing with faint, moving targets, what you see often depends on how you look. Most observers stack their images to follow the comet's motion, letting the background stars trail into lines of light. It's a standard method to improve the signal, but it can also mask delicate structures like tails. And so, the debate began. Does Borisov truly lack a tail, or have we just not looked closely enough? There was something almost poetic about the parallel. 2 travelers, both seemingly without tails, both bathed in sunlight yet refusing to glow as expected. Two visitors that didn't quite behave like the icy emissaries from our own solar system. In their restraint, they seemed to hint at something older, colder, forged in places far from the warmth of any star. Perhaps, you might think, they carried within them the chemical memory of other suns, other times. But before the poetry, there is the data. Astronomers began to chart their positions, drawing fine arcs across the celestial sphere. 3I Atlas, already well studied, followed a hyperbolic path, meaning its eccentricity was greater than 1. In simple terms, it was not bound to the sun's gravity. It had come from elsewhere and would leave forever. Its trajectory, after swinging past perihelion, was now bending outward toward the orbit of Jupiter, escaping into the night. C 2025, V1 Borisov, on the other hand, was just arriving from below the plane of the ecliptic, that thin sheet where most of the planets circle. It was climbing upward toward the northern sky, tracing a path that, on our maps, brought it near the constellation of Virgo, not far from Atlas's position. For observers on Earth, the coincidence was striking. To see two interstellar objects, apparently near each other in the sky, within months of discovery, was something that invited speculation. Could it be random? Almost certainly. Yet, as scientists, we cannot rest on almost. We need to test. Was there a deeper link, a shared trajectory, perhaps even a shared origin? Or was this merely the cosmic equivalent of two ships appearing to cross paths on a distant ocean, their sails illuminated for a brief, coincidental moment? To answer that, we must turn to the subtle art of measuring distance. The coordinates we assign to stars and comets, right ascension and declination, tell us direction, not depth. They are, essentially, the longitude and latitude of the sky. To know where something truly lies, we need parallax, tiny shifts in position caused by Earth's motion, or a chain of precise astrometric measurements over time. Only then can we reconstruct the three-dimensional story. That's why the coming weeks after the discovery were so crucial. Each new image, each refined orbital fit, helped transform the mystery of between into something we could test. And still, even as data accumulated, the mood among observers was one of quiet wonder. Tianwen, the Chinese spacecraft, released low-resolution images, showing 3I Atlas as a soft blur against the starfield. Other telescopes reported brightness fluctuations, small but consistent. Some speculated that rotational jets, subtle outgassing vents on the nucleus, were pulsing in cycles. Others thought the changes might simply be due to geometry, how the sun's light scattered off irregular dust grains. Whatever the cause, the object seemed alive, not static. And that, you see, is what keeps us watching. C 2025 V1 Borisov, meanwhile, remained elusive. Its coma shimmered faintly, its nucleus too small to resolve. Was it truly a comet, or perhaps a more primitive body, rich in carbon compounds that darkened its surface? Could the faintness of its tail mean that it was composed of larger dust particles, less efficient at scattering sunlight? Or maybe it was releasing gases other than water, carbon dioxide or carbon monoxide, substances that can drive early, the activity far from the sun, but produce less visible display. These were not idle musings. They hinted at the physical conditions of the place where the object was born, perhaps a region colder than any part of our solar system. Somewhere in this web of possibilities lies the essence of why these discoveries matter. Each interstellar object carries within it a record of processes that happened around other stars billions of years ago. Their orbits are messengers, their compositions are archives. And yet, even as we study them with spectroscopy and photometry, we must also navigate the limitations of our own instruments, the tricks of perspective, the biases of detection. For instance, why do we seem to find several of these objects clustered in similar parts of the sky? Is it truly a stream, a flow of interstellar debris passing through our neighborhood? Or is it that we simply observe more carefully there, turning our telescopes toward those regions because of convenience or habit? Statistics, you see, can play strange games with meaning. As for the brightness anomaly of Atlas, that unexpected increase after perihelion, it became a small mystery of its own. Normally, comets fade predictably as they move away from the sun, their sublimating ices freezing back into stillness. But Atlas refused to dim as quickly as expected. Some proposed that volatile ices, like carbon monoxide or carbon dioxide, which sublimate at much lower temperatures than water, continued to feed its coma long after the main heating had passed. Others suggested that the comet's geometry, the way its surface faced the sun, could have created a focused jet or reflective plume that temporarily enhanced its light. And still others thought of dust, coarse, heavy grains that scatter light differently, keeping the object visible longer. You might ask, why does it matter? Because each deviation from the expected is a clue. It tells us that nature is more varied than our models assume, that the building blocks of planets and comets may not all share the same story. And perhaps that interstellar space itself is not as empty as we once believed. Imagine, then, the scene from a distance. Earth turning quietly under a November sky, telescopes tracking faint points in Virgo, data lines humming across networks from observatory to observatory. Two objects, small beyond comprehension, yet vast in what they represent, gliding through the gravitational field of our Sunday, one on its way in, one on its way out. And somewhere, between them, at least to our eyes, hangs a question. Could there be more to this alignment than chance? Might these two travelers be fragments of a single ancient event, a breakup that scattered them across interstellar space? Or is it our human mind, ever searching for patterns, that sees connection where there is only coincidence? Science begins with such questions, but it demands that we resist easy answers. To claim a shared origin, we would need precise spectroscopy, comparing their chemical fingerprints and long arcs of astrometry to reveal whether their trajectories truly echo one another. For now, all we have are hints. Still, hints are where wonder lives. When I think of Borisov approaching its closest pass to the Sun, climbing out of the shadowed regions below the ecliptic, I imagine it as a messenger emerging from the deep. Perhaps it carries with it grains older than Earth itself. Perhaps, somewhere within its darkened nucleus, lies material that once orbited a distant star whose light will never reach us. And Atlas, receding but glowing softly, becomes its silent counterpart, fading into the dark beyond Jupiter's path. In a way, they form a kind of mirror. One enters as the other leaves, like a breath drawn in and released. Between them, our tiny world watches, measures, wonders. We chart their paths with equations, but what we truly seek is meaning. What does it tell us that two such visitors appear almost together? Are we witnessing the edges of a galactic current, a flow of matter stirred by ancient stellar explosions? Or is it just our moment in time, our brief coincidence with their endless voyage? And so, as the nights of November grow longer and the data deepens, astronomers continue to trace their movements with patient precision. Each coordinate, each photon, adds to the growing picture. The next step, naturally, is to move beyond this question of where, to explore the deeper geometry that underlies what we see. Because to understand what it means for something to be between, we must look beyond the flat sky and into the vast, layered architecture of space itself. And that, I suppose, leads us to the next chapter of this strange interstellar story. When we speak of something lying between in astronomy, we must first confront the illusion of our own perception. You see, when we look up, we are not seeing depth, we are seeing direction. The night sky is a vast projection, a kind of celestial map painted on the dome of our sight. Every dot of light seems near every other, simply because the heavens do not reveal their distance to us. And that, perhaps, is where the confusion begins. If you were to draw a line through Earth, through Borisov, and outward toward Atlas, the picture might appear beautifully simple. 3 points neatly arranged in space, an arrow of cosmic geometry. But reality, well, reality resists simplicity. For while Borisov seems to lie between us and Atlas in the two-dimensional projection of the sky, it is in fact climbing upward from below the plane of the solar system. Its path crosses the sun's equatorial sheet at an angle, and by the time it reaches its closest pass, it will sit above the ecliptic. Atlas, on the other hand, is already moving outward, still within the plane, but far from the Sunday. So when our telescopes frame them together, It is the trick of perspective to travelers whose roads happen to overlap in our line of sight, though they roam in very different regions of space. This distinction between appearance and geometry is not trivial. In astronomy, the difference between direction and distance can transform meaning entirely. We use coordinates called right ascension and declination, celestial equivalents of longitude and latitude, to specify where something appears in the sky. But these coordinates tell us nothing about how far away it is. To reveal that third dimension, we rely on time and on motion. We measure how the position of an object shifts slightly as Earth orbits the Sun, a tiny displacement known as parallax. Or, for faint comets and asteroids, we observe their changing angles against the background stars night after night, calculating their orbits by tracing the curve of their movement. From such small differences, entire distances emerge. So when astronomers say they will reconstruct the geometry of the event, this is what they mean. They will combine long sequences of measurements astrometry from different observatories across the globe to see whether the alignment of Earth, Borisov, and Atlas is genuine or only apparent. In theory, if Borisov were truly between us and Atlas, then their paths might intersect not just in projection but in physical space, separated by a measurable and perhaps even narrow corridor of distance. But if the orbits never come near each other, then between becomes a word of perspective only, a trick of the cosmic lens. There are ways to test this, though each is delicate. One idea is photometric correlation, searching for synchronized fluctuations in brightness between the two objects. If Borisov were ever to pass directly in front of Atlas from our viewpoint, even at vast distances, we might detect a faint dimming, a momentary dip in light, as one body briefly occludes the other. This would be an extraordinary coincidence, and the change would be so subtle that only the most sensitive instruments could notice it. But such events, if recorded, can confirm true alignment in 3 dimensions. Another test lies in timing and orientation. Astronomers track the direction of each object's coma, the faint envelope of gas and dust that surrounds its nucleus, and the axis of any asymmetry within it. If those directions correlate with their changing apparent positions relative to one another, it could suggest interaction. Perhaps the radiation pressure or solar wind pattern they share is modulated by their geometry. But if no such correlation appears, the case for physical connection weakens. Then comes spectroscopy, the deep fingerprint of light. Every atom and molecule absorbs and emits light at characteristic wavelengths, leaving patterns of lines across the spectrum. By comparing the spectral features of Borisov and Atlas, scientists can look for shared signatures, bands of carbon or cyanide, perhaps traces of more exotic compounds. If the ratios match too closely to be coincidence, it might hint at a shared environment of origin. Yet if they differ sharply, one rich in volatile carbon dioxide, the other depleted, it would argue for separate births under different stellar chemistries. And so the inquiry unfolds layer by layer, each observation peeling back one illusion to test another. The brightness of Atlas remains a small enigma. Why does it continue to shine more intensely than predicted, even as it moves away from the Sun? We know that the solar wind was strong this season, carrying flares and coronal mass ejections outward through interplanetary space. Yet the comet's surface appears almost indifferent, showing no great tail. One explanation is compositional, the possibility that its surface is dominated by ices that sublimate not into visible water vapor, but into invisible carbon gases, producing less scattering dust. Another is geometric. If the comet's jets point away from us, or if we observe it nearly along the axis of its tail, the emission could be hidden by angle alone. The third is mechanical, that the dust grains are unusually large, suppressing light reflection. Borisov too raises similar puzzles. Its coma brightens modestly, but no tail stretches far behind. If these 2 comets share this peculiarity, is it coincidence, or the echo of a deeper kinship? Could it be that both are remnants of an ancient stellar system where sunlight never grew strong, where comets evolved under dimmer warmth and therefore developed surfaces resistant to heating? The truth may lie in the ratios of their gases, the way their spectra dance under sunlight, but those measurements take time. The geometry of the situation, though abstract, holds emotional power. Imagine Earth as a moving observatory, orbiting at 30 kilometers per second. From this whirling platform, our telescopes trace two faint wanderers, one receding, one approaching. Each night, the angles shift slightly, the illusion of alignment slowly dissolving. The phrase "between Earth and Atlas" begins to lose its poetic neatness, replaced by the messy, beautiful reality of celestial mechanics. You might wonder, could there be a dynamic corridor between them? A shared region of interstellar space that guides their motion, like a river channel carved by gravity or magnetic fields? In principle, such corridors do exist. The interstellar medium is not uniform. It is shaped by the remnants of supernovae, by waves of compressed plasma, by the great arcs of the galaxy's magnetic field. Through these structures, dust and debris might flow, much as ocean currents guide plankton across the sea, but proving that any two specific objects follow such a current would be exceedingly difficult. We would need not only trajectories, but velocities, chemical affinities, and perhaps even isotopic ratios. Still, the notion lingers: two travelers, passing through the same invisible stream, bound not by gravity, but by the lingering momentum of their birth long ago around another sun. You see, the idea that matter can drift across the galaxy, carrying with it the story of a different world, is both scientific and profoundly human. It reminds us that our solar system is not isolated, it is porous, connected to the broader cosmic ecosystem. Every interstellar visitor, whether Oumuamua, Borisov, or Atlas, is a fragment of that grand exchange. The measurements we make now, angles, magnitudes, spectra, are our way of reaching into that mystery. Yet, there's humility in recognizing how small our instruments still are compared to the distances they probe. A single degree of error in parallax can mean millions of kilometers of uncertainty. The faintest deviation in light curve could come from a thermal crack or a camera artifact. To distinguish signal from illusion requires patience, repetition, and the willingness to doubt even our own best interpretations. That's the heart of science, the discipline of uncertainty. We do not seek certainty as much as convergence, a gradual narrowing of possibilities until what remains, though incomplete, is at least consistent. So when astronomers say we cannot yet label the alignment as physical, they are not being evasive. They are honoring the distance between what we see and what we know. If Borisov and Atlas are indeed unconnected, their chance alignment would still carry value. It gives us two laboratories to compare side by side, two interstellar messengers illuminated by the same sun, revealing how different materials react under identical conditions. By watching how their comas evolve, how their brightness fades or steadies, we can test theories of sublimation, dust cohesion, and compositional diversity. Even coincidence, in the cosmos, can be fertile ground for discovery. Perhaps the most compelling challenge ahead lies in time itself. The key to decoding geometry is patience. Each night of observation extends the arc of known motion, reducing uncertainty. With every new measurement of position, the three-dimensional model sharpens. Eventually, the equations that describe their orbits will intersect or diverge decisively. Only then will we know whether between is a physical truth or a poetic mirage. But even the mirage has meaning, because in those moments of apparent alignment, when two faint bodies seem to share the same sky path, we glimpse the hidden complexity of perspective. The universe constantly reminds us that our view is local, that the straight lines we see are almost never straight in space. The illusion of closeness is itself a teacher, whispering that truth often lies just beyond the reach of our first impression. And that's the beauty of it, this slow unraveling, this patient peeling back of illusion. As data flows in from observatories scattered across continents, from space telescopes orbiting far above, the picture of Borisov and Atlas grows less about coincidence and more about context. Whether they are distant strangers or faint cousins, their shared moment in our sky has already expanded our understanding of how vast and how intricate this cosmic stage really is. Still, there is one question that lingers, hovering like a spark between all these calculations. If not alignment, then what? What invisible forces draw such objects near our sun at this moment in time? Are we simply witnessing the random scatter of galactic debris? Or is there some larger rhythm, a resonance, perhaps, that governs when and how these travelers arrive? To answer that, we must step even further back, beyond geometry and observation, into the realm of dynamics and origins. So then, before we chase the rhythm of their arrivals, we must ask the most fundamental question: what exactly is an interstellar visitor? What makes an object not of our solar system, but of another, born under a different sun? It sounds simple, yet the boundary between native and foreign is written not in color or shape, but in motion. You see, every object bound to the sun, planet, asteroid, comet, follows an ellipse. It may be stretched thin, it may wander far, but an ellipse always closes. A hyperbola, however, does not. When an orbit's eccentricity rises above one, the curve never folds back upon itself. It opens outward, a path of no return. That is the first signature of the interstellar. And so, when astronomers detect a body on a hyperbolic trajectory, they pause. They calculate again and again, testing whether the curve is real or merely an illusion of measurement. Because a single error in velocity can transform a visitor into a prisoner. But when the data holds steady when the object's speed at infinity, what we call its asymptotic velocity, remains above the solar system's escape threshold, then we know we are watching something rare. It is not a comet of our own sun, but a traveler from elsewhere, one that has fallen through our cosmic neighborhood by chance. The first time we saw such a visitor was in the autumn of 2017. It was given a name both poetic and precise, one Oumuamua. In Hawaiian, it means a messenger from afar arriving first. And truly, it was. Unlike any comet or asteroid we had catalogued, it flashed briefly across the solar system and was gone before we could aim most of our instruments. Its light curve fluctuated in a strange rhythm, suggesting an elongated shape, perhaps cigar-like, perhaps pancake-flat. It showed no coma, no outgassing, no visible tail. Yet it accelerated slightly, as if something unseen were pushing it. That tiny, unexplained acceleration became one of the most debated mysteries of the decade. Could it be a jet of gas invisible to our telescopes, a result of uneven sublimation on its surface? Or was it something more exotic, a reflection of radiation pressure on a structure thinner than any rock, perhaps a sheet of material that responded to light itself? For months, speculation ran wild. But you see, the truth may simply be that our models of cometary activity were incomplete. Even small variations in thermal conductivity or albedo could create forces subtle enough to mimic that anomaly. Still, Oumuamua reminded us that interstellar space might contain things we have not yet imagined. Then, 2 years later, came another messenger to V1 Borisov. This one behaved more like a classical comet, with a bright coma and a faint tail that spread in the cold light of the Sunday. Spectroscopic observations revealed cyanide and carbon monoxide, molecules familiar to our own comets, but in unusually high ratios. Borisov, the second interstellar visitor, was like a confirmation, a sign that Oumuamua had not been a fluke. The galaxy, it seemed, was sending us fragments of other worlds, each carrying clues about where they were formed. From these two, we learned something profound, that interstellar space is not empty. It is seeded with debris, broken shards of planets, ices from frozen orbits, remnants of early solar disks flung outward by gravitational dances around young stars. Each hyperbolic visitor is a story of loss and motion, of worlds that built and unbuilt themselves long before we existed. When we trace their orbits backward, they do not converge on any known system. Their paths are blurred by time, stretched by the random tugs of galactic tides. But statistically, their presence tells us something about the Milky Way itself, that planetary systems everywhere are restless, shedding fragments that wander between stars for millions, even billions of years. Now, in 2025, with the appearance of 3I Atlas and the new C 2025 V1 Borisov, we are seeing the continuation of that story. A third and perhaps fourth chapter, each offering a new variation on what it means to be from beyond. And again, the question rises, how do we know? The answer lies in velocity, an object moving faster than the sun's gravitational hold, roughly 42 kilometers per second, at the distance of Earth, cannot be captured unless it loses energy through an improbable interaction. When Atlas was first measured, its orbital eccentricity exceeded 1, and its speed at infinity was calculated around 30 kilometers per second relative to the sun's rest frame. There was no doubt it had come from the interstellar medium, entered our system, looped near the Sun, and was now departing forever. The beauty of this is that it allows us to reconstruct, even faintly, the visitor's home. By mapping its direction of arrival, astronomers can trace which region of the galaxy it likely came from. Oumuamua approached from near the solar apex, the direction the Sun moves through the galaxy, suggesting it was part of the general background of interstellar debris. Borisov arrived from a different region, near the constellation Cassiopeia, perhaps from a young stellar association rich in volatile material. Atlas entered from Virgo, almost the same quadrant of the sky where our own motion through the galaxy projects forward. Whether this means these objects belong to a shared galactic stream is still uncertain, but the alignment is, at the very least, curious. When we speak of streams, we borrow language from fluid dynamics, but the analogy holds. The galaxy, with its billions of stars, is a gravitational ocean. Every system flings out small bodies during its early years: comets, planetesimals, icy rocks. These wander through space, influenced by galactic tides, by passing stars, by the faint drag of interstellar gas. Over millions of years, their random motions blur into slow, coherent currents. We may be drifting through one of those now, a region where interstellar objects happen to be denser, giving us this rare window of observation. And yet, not all interstellar bodies are alike. Some, like Oumuamua, seem dry, possibly devolatilized, their ice is long, gone. Others, like Borisov and perhaps Atlas, retain active surfaces. The diversity suggests different histories. A body ejected early from a hot, inner system would lose its volatiles quickly, becoming inert. One expelled from a cold outer orbit might preserve its ices for billions of years, awakening again only when touched by the light of a new star. That, in a way, is what makes each encounter precious. When we observe a brightening coma, we are watching chemistry from another sun flare to life under ours. But there's another reason these hyperbolic visitors matter. They test our understanding of the forces that shape motion in the solar system. For instance, when we measure small deviations from purely gravitational paths, we are forced to account for non-gravitational accelerations, jets of gas, asymmetric radiation, or fragmentation events. These forces, though tiny, can tell us about the internal structure of the body, how porous it is, how heat flows through it, whether it spins chaotically or stably. In the case of Atlas, preliminary data show less non-gravitational acceleration than expected, implying its outgassing is weak or evenly distributed. Perhaps its surface is coated in refractory material that seals in the ices below. Perhaps it is simply too cold for vigorous activity. Interstellar objects also provide a test for the chemistry of formation. By comparing their spectral fingerprints with those of solar system comets, we can infer how universal certain compounds are. The presence of cyanides, for instance, hints that nitrogen-bearing organics form easily in many environments. The detection of carbon monoxide points to regions of birth colder than Neptune's orbit. If two unrelated interstellar comets share similar ratios of such molecules, it suggests that the processes that shaped our solar system are not unique. The universe builds worlds according to familiar blueprints. But, perhaps most striking of all, these visitors remind us that the boundaries between systems are porous. Over eons, the galaxy trades matter. Dust from distant stars falls onto our own planets. Comets from other suns drift past our detectors. In that sense, the Milky Way is not a collection of isolated islands, but a single archipelago of exchange. Our own solar system likely contributes to this traffic as well. Each time Jupiter or Saturn slingshots a comet outward, some fraction of those bodies escape entirely, becoming interstellar wanderers themselves. Someday, another civilization may study one of our fragments as it drifts through their skies, just as we now study these. That thought carries a quiet beauty, doesn't it? The idea that even when we vanish, pieces of our world will continue their journey, bearing chemical traces of the sun that once warmed them. In the long arithmetic of time, every system gives and receives. Matter, in its endless migration, becomes the thread that sews the galaxy together. Still, not every hyperbolic orbit guarantees an interstellar origin. Occasionally, strong gravitational encounters within our own solar system can fling comets outward at near-escape velocity. A close pass with Jupiter, for instance, can distort an orbit enough to mimic interstellar motion for a brief time. That's why astronomers analyze the inbound trajectory as well as the outbound one. If the eccentricity exceeds 1 even before the object's first close approach to any planet, then the case is solid. If it only appears hyperbolic after interaction, it may simply be a local comet on its way out. In Atlas's case, the hyperbolicity existed from the beginning. Its speed too high, its angle too wide. It was never one of ours. And so, through these layers of evidence, velocity, eccentricity, incomposition, we begin to paint the portrait of a class of objects that bridge the vast gulfs between stars. But the story does not end with identification. The deeper question, the one that keeps astronomers awake at night, is how such bodies are launched in the first place. What catapult hurls a frozen worldlet from its home into the void? The answer lies in the chaos of formation. In the youth of a planetary system, when giant planets migrate and collide, their gravity acts like a slingshot. Thousands of comets and asteroids are thrown outward, some into distant orbits like our own Oort cloud, others beyond it entirely. These become interstellar seeds, drifting through the galaxy until chance brings them near another star. Some may be accelerated by supernova shocks or by the passage of dense molecular clouds. Over time, their trajectories are randomized, turning the Milky Way into a soft haze of invisible travelers. We are only now beginning to glimpse them. Our telescopes, sensitive enough to detect faint moving points, have opened a window into that hidden population. What we once thought was emptiness is, in truth, a subtle rain of visitors. And if this is true, if the galaxy teems with such wanderers, then each one is a sample of another world's geology and chemistry, drifting freely for us to study. We do not need to send probes across the stars send their fragments to us. And so, when we ask what makes a visitor interstellar, we are not merely defining an orbit, we are recognizing a pattern of exchange, a cosmic dialogue written in motion. These objects are both scientific data and philosophical reminder that everything moves, that nothing remains bound forever. Even the sun, one day, will lose its grasp on the outermost comets, letting them drift into that same galactic sea. The next logical question, then, is one of substance. If we now understand how these visitors move, what they are, and why they matter, the next mystery is how they behave, how they awaken under sunlight, what drives their strange luminosity, and why some shine without tails while others erupt into plumes. That mystery belongs to the physics of activity, the dance between ice and light, heat and distance. And that, well, is where our journey naturally turns next. If we are to understand these visitors, Borisov, Atlas, and the countless others still hidden beyond Neptune's shadow, we must first grasp how a comet lives, and more curiously, how it wakes. Because, you see, not all comets wait for the warmth of the inner solar system to stir. Some begin their transformation long before sunlight grows strong, when they are still distant, cold, and half asleep. That, perhaps, is the most mysterious part of all, how something frozen for eons begins to breathe again across billions of kilometers of space. In our own solar system, most comets sleep in the dark reaches of the Kuiper belt or the Oort cloud. There, they rest in deep freeze, composed primarily of water ice mixed with dust, organics, and more volatile compounds like carbon monoxide and carbon dioxide. When they fall sunward, the story usually unfolds in familiar rhythm. At first, little happens. The sunlight is too weak to stir the water ice. It remains solid, locked in its crystalline calm. Only as a comet crosses the orbit of Jupiter or Mars does it warm enough for water to sublimate, that is, to turn directly from solid to gas. The vapor escapes, carrying dust into space, and a coma blossoms around the nucleus. That's when the comet truly awakens, forming the luminous tale that poets and astronomers alike have adored for centuries. But interstellar comets like C 2025, V1 Borisov, and 3I, Atlas, seem to break this pattern. They exhibit signs of activity, even at distances where water ice should remain inert. That tells us something profound. The energy driving their awakening does not come from water, but from more volatile substances that evaporate at far lower temperatures. Carbon monoxide, for instance, begins to sublimate when the sunlight is still faint, far beyond the orbit of Saturn. Carbon dioxide follows soon after. Both gases can escape from a comet's surface while it is still distant from the sun, producing faint comet that shimmer like ghostly halos long before water joins the dance. This early activity, you see, is not just a curiosity, it is a signature. It tells us about where these objects were born. If a comet shows strong CO and CO2 sublimation but little water-driven behavior, it likely formed in a region of its parent system far colder than anything in our solar system's early disk. Such places exist only in the outermost reaches of protoplanetary clouds, where sunlight barely penetrates and temperatures remain dozens of degrees above absolute zero. There, volatile molecules freeze easily, locking into ice mantles that survive for billions of years. To see such ices survive intact means we are looking at material forged in the coldest cosmic foundries, places perhaps orbiting dim red stars, or cast adrift after the collapse of stellar nurseries. That's the wonder of early comet activity. It's not merely physics, it's a kind of archaeology of formation. Every puff of gas, every molecule escaping into space, is a clue to the temperature and chemistry of a long-lost world. When astronomers measure the ratios of gases, say, CO to H2O or Cn to C2, they are reading the ancient weather of another star system. A high CO ratio hints at an origin beyond the frost line, where even carbon monoxide can freeze. A low ratio, dominated by water, points to warmer, inner regions. So when we say Borisov is active at large distances, what we really mean is that it was born in a colder cradle, perhaps one that never saw a bright sun at all. Now, to imagine how this happens physically, think of the comet's surface as a layered crust of dust and ice. Beneath lies a complex interior, porous, spongy, riddled with pockets of volatile material trapped during formation. When the sun's rays begin to strike, even weakly, heat seeps inward. The uppermost layer may remain cold, but below it, small reservoirs of carbon monoxide or carbon dioxide begin to vaporize. The gases push outward, seeking escape. When they find cracks or weak spots, they vent into space, carrying fine grains of dust along with them. This creates a diffuse, bluish haze, what we call the coma. Water, by contrast, remains dormant until the comet nears 2 or 3 astronomical units from the sunday. By then, the earlier activity may have already reshaped the surface, exposing new regions or sealing others. So, the very first signs of life in a distant comet are not from water, but from these invisible, ghostly vapors of CO and CO2 substances that speak of the deep cold between stars. In the case of 3I Atlas, this explanation fits beautifully. Its brightness increased as it approached perihelion, but its activity seemed subdued compared to a typical water-driven comet. No spectacular tail, no violent jets, just a soft, persistent coma glowing with unexpected brightness. That discrepancy between luminosity and visible activity hints at a composition rich in low-temperature volatiles. In other words, Atlas was breathing carbon monoxide, not water vapor. The same might be true for C-2025, V1 Borisov. Observers have noted faint outgassing at distances where water ice should still be inert. Some spectra show weak emission lines near the wavelengths associated with CO, though the data remains sparse. If confirmed, it would place Borisov firmly among that class of ultra-cold comets' bodies that awaken early because their chemistry demands so little heat. It's worth pausing here, because this is where the story deepens. If these objects indeed formed in extremely cold environments, they may hold the most pristine samples of interstellar chemistry available to us. Imagine that tiny grains and frozen molecules that have never been warmed, never been processed, since the time of their creation. In them, we could find the seeds of complex organics, the same, precursors that once fell on early Earth to spark prebiotic chemistry. Each interstellar comet might thus be both a messenger and a relic, a preserved chapter of the galaxy's own evolutionary history. Yet, there's something paradoxical about this, isn't there? To survive the journey between stars, a body must endure countless collisions and radiation storms. and yet these interstellar travelers still contain fragile ices, easily destroyed by heat. How can both be true? The likely answer lies in shielding layers of dust and refractory compounds that form a kind of natural armor. Over time, cosmic rays darken these surfaces, turning them into carbon-rich crusts that protect the volatile heart within. When sunlight finally warms them again, they respond sluggishly, releasing gases not in violent bursts but in soft, persistent flows. That may be why both Borisov and Atlas lack clear tails. Their activity is muffled, filtered through ancient soot. You might picture it as a frozen lung, breathing faintly in the sunlight. Each vent is a whisper from deep time, and as the gas escapes, it carries not just dust but information. Spectroscopy can reveal isotopic ratios: carbon 1,2 to carbon 1,3, oxygen 1,6 to oxygen 1,8, tiny signatures that tell us whether the comet's materials were forged near massive stars or in quiescent molecular clouds. The proportions of nitrogen and carbon compounds can hint at the radiation field that bathed its parent nebula. In that way, every outgassing event becomes a message, written in vapor rather than ink. But there's another question. Why does early activity vary so much between comets? Why do some awaken far from the Sun, while others remain silent until they cross Mars's orbit? The answer lies partly in texture. A comet's porosity, the size and connectivity of its internal pores, controls how easily heat and gas move. A dense nucleus with few pathways will remain dormant until strong heating penetrates deeply. A porous one will leak gas early and often. Rotation matters too. As a comet spins, sunlight alternately warms and cools its surface, driving cycles of stress that open cracks and release trapped material. Even the angle of rotation relative to the Sun can determine whether we see jets or nothing at all. All of this means that when we observe differences between Atlas and Borisov, we are not seeing random quirks, but fingerprints of their internal architecture. One may be more porous, one more compact. One may rotate rapidly, exposing multiple vents. The other may turn slowly, presenting the same sealed face for weeks. The geometry of sunlight and the grain size of dust both shape the visible outcome. That is why early comet activity remains one of the most complex and revealing phenomena in planetary science. It is the language through which comets speak of their birthplaces. And perhaps, beyond the science, there's something deeply human in this image of awakening. A body traveling for millions of years through darkness, untouched, frozen in silence, until, at last, the faint light of another star begins to stir it. Slowly, almost imperceptibly, it breathes again. What does that say about persistence, about the memory of matter? That even in the coldest voids, the potential for renewal endures, waiting only for warmth. Still, for scientists, poetry must yield to measurement. The challenge now is to quantify this behavior. How much CO or CO2 is required to produce the observed brightness? How does the gas flux change with distance? To answer, astronomers combined photometric data with thermal models, simulations that track how sunlight penetrates, how heat diffuses, how pressure builds beneath the surface. In these models, a small increase in volatile abundance can shift the onset of activity by billions of kilometers. That's why even modest differences in composition can transform a silent rock into a glowing wanderer long before it nears the Sunday. And yet, even our best models struggle with the fine details. We still don't fully understand how microfractures propagate, how dust grains interact with gas flow, or how radiation alters the surface over long timescales. These are the frontiers of comet science, where observation and theory meet in uncertainty. But that's precisely what makes Borisov and Atlas so valuable. They expand the parameter space. By comparing their early activity with that of homegrown comets, we refine our understanding of what drives sublimation under extreme conditions. Eventually, with enough such visitors, we may even map the diversity of interstellar ice. Perhaps we will find families of composition, clusters of chemistry that point to distinct regions of the galaxy. Some may be born in carbon-rich systems, others in nitrogen-poor ones. Their early behavior, how soon they awaken, how bright they grow, will tell us not just about themselves, but about the distribution of life's raw ingredients across the Milky Way. And that thought, well, it leads us naturally to the next puzzle. Because if we can learn so much from the steady breath of a comet, what might we learn from its heartbeat, the subtle flickers and surges in its brightness that reveal its inner pulse? Beyond early activity lies a world of variability, of sudden outbursts and mysterious dimming. They are the comet's signals, written in light rather than gas. And so, from the slow awakening, we now turn toward the rhythms of change, the language of light itself. Light is a language, you see, and comets speak it fluently. But unlike the steady glow of stars, their light is restless. It flickers, it breathes, it trembles in ways that can seem unpredictable, almost emotional. When we study a comet's brightness over time, we create what's called a light curve, a record of its heartbeat, a rhythm of energy and shadow. In these curves, astronomers read the story of rotation, jets, fractures, even moments of collapse. Every small fluctuation holds a clue to what's happening on the surface of a distant, spinning world of ice and dust. For comets like 3I Atlas and C 2025 V1 Borisov, these light curves are especially valuable. They help us sense what the eye cannot see. Because from Earth, a comet is nothing more than a point of blurred light, its nucleus, a speck smaller than a pixel even in powerful telescopes. The changes in brightness, those tiny surges and drops, are our only way to hear the object's voice across space. And what's remarkable is how alive that voice can be. A comet's light can vary for many reasons. Some are gentle, periodic pulsations caused by rotation. As it spins, different regions of its surface turn toward the sun, each with its own reflectivity and activity. Dusty areas brighten, darker patches fade. Over time, this creates a cycle of brightness, repeating every few hours or days, depending on how quickly the nucleus rotates. Others are sudden and sharp, the result of outbursts, brief eruptions of gas or dust that can make a comet flare dramatically, as though exhaling after long restraint. These outbursts are both thrilling and elusive. They may arise when sunlight penetrates a deep crack, reaching a reservoir of volatile ices that suddenly vaporize. The trapped gas builds pressure until the overlying crust gives way, releasing a jet of material that expands and glows. Sometimes, thermal stress from repeated heating and cooling can fracture the surface, triggering localized avalanches that expose fresh ice. In each case, the comet brightens swiftly, then fades as the gas disperses. When plotted over time, these changes form the comet's light curve, a kind of fingerprint. A smooth, regular pattern suggests rotation. A jagged, erratic one suggests activity or instability. But interpretation is an art. The human eye loves patterns, even where none exist. To read a light curve properly, scientists compare it across multiple wavelengths, separating dust reflection from gas emission. They use polarimetry to detect how the light scatters, which reveals the size and composition of the particles in the coma. Every method adds another brushstroke to the portrait of the comet's behavior. For interstellar comets like Atlas and Borisov, these patterns may reveal not just their motion, but their very nature. If their light varies periodically, we can infer their rotation period, perhaps 5 hours, perhaps 10. If it varies irregularly, it may suggest chaotic tumbling, a sign that the object is irregular in shape or experiencing uneven outgassing. Oumuamua, for instance, displayed a dramatic brightness variation tenfold between peaks and troughs, implying an elongated tumbling form. Its motion was so complex that no single rotation period could describe it. Perhaps Atlas and Borisov, too, hide similar complexity, their brightness dancing to rhythms we have yet to decode. But beyond geometry lies chemistry. The ratio of dust to gas expelled during an outburst can change the brightness curve in subtle ways. Dust reflects sunlight, gas glows by emission. A dust-rich jet creates a warm, steady glow, while a gas-rich burst flares blue and fades quickly. By monitoring the color evolution of a light curve, astronomers can tell what kind of material is driving the change. In that way, light becomes a chemical code, a way of inferring composition across unimaginable distance. Then there are the quiet fluctuations, the micro-variations too small for the naked eye, but visible to sensitive instruments. These are perhaps the most telling of all. They may indicate small, repeating jets that pulse with the comet's spin, or shadowed areas emerging into light. In some cases, they may even hint at internal instability, a slow rhythmic breathing as subsurface gases migrate through porous layers. Comets, after all, are not solid in the way we imagine. They are more like fragile foams of ice and dust, riddled with voids. Heat and pressure move through them like weather, creating their own kind of microclimate. For 3I Atlas, early photometric data showed small but consistent fluctuations in brightness, roughly synchronized with its apparent rotation. Some observers thought these might correspond to localized jets emerging from specific latitudes, perhaps venting CO2 through narrow fissures. Others proposed that the pattern was purely geometric, the effect of sunlight reflecting off an elongated nucleus as it tumbled. Either way, the result was the same, a rhythmic pulse of light, soft yet steady, like a heartbeat echoing across millions of kilometers. C. 2025 V1 Borisov, in contrast, appeared steadier, almost tranquil. Its light remained stable over long intervals, with only faint evidence of short-term variability. This could mean one of two things. Either its rotation axis is oriented nearly toward Earth, so we see little change as it spins, or its activity is evenly distributed, with no dominant jets. If true, it would suggest a remarkably uniform surface, an unusual trait among comets. Or perhaps, and this is an intriguing thought, the brightness fluctuations exist but are hidden by the way we observe. When astronomers stack multiple images to reduce noise, they smooth away small variations. In doing so, they also erase the comet's subtler rhythms. Light, then, is both a revelation and a deception. It gives us everything we know about these travelers, yet it hides the details behind layers of distance, instrument, and perception. To interpret a light curve correctly, one must balance mathematics with intuition. A sudden spike could be a real outburst, or simply an artifact of atmospheric interference. A fading trend might mean dwindling activity or changing geometry. In that sense, each comet's light curve is like a musical score, one that requires not just observation, but listening. When comets experience true outbursts, the results can be spectacular. Some brighten by several magnitudes in a single night, releasing millions of tons of dust. The coma expands rapidly, scattering sunlight and producing a diffuse, milky glow. Within days, the brightness fades as the particles drift outward. On rare occasions, the stress of these eruptions can fracture the nucleus entirely, splitting the comet into fragments. Such events have been observed in homegrown comets like 73P Schwarzmann-Wachmann, but could they occur in interstellar ones as well? It's possible, though no such fragmentation has yet been confirmed. Still, the faint variability of Atlas hints that below its surface, forces of expansion and contraction may already be at work. These changes are not random, they follow the subtle interplay between sunlight, rotation, and structure. When one side of a comet warms, ices sublimate, pushing gas outward. The escaping gas exerts a tiny thrust, altering the spin. Over time, this can accelerate or decelerate rotation, changing how the nucleus presents itself to the sunday. This feedback loop, sunlight driving motion, motion altering sunlight, is what gives a comet its dynamic character. It's almost like watching weather form on a world without atmosphere. And then there are the microbursts, fleeting increases in brightness that last only hours. These may be caused by localized vents that open and close as the nucleus rotates, releasing small plumes of gas. Think of them as sighs in the comet's slow respiration. Each one subtly reshapes the coma, mixing fresh dust with older material. If we could watch closely enough, we'd see the coma breathing, expanding and contracting in rhythm with its internal pulse. You know, there's something poetic in that. These frozen relics, adrift for eons, still move with such vitality, responding to light like living organisms. They absorb, react, adapt. In a sense, they remind us that energy is the universal, a signature of life, not life in the biological sense, but in the dynamic, cosmic one. Wherever energy flows, patterns emerge, and those patterns, through light, become legible. That's why astronomers treasure light curves. They are not just data, they are diaries. Each one captures the intimate relationship between a comet and its star. And when we compare them across different objects, we begin to see families of behavior. Some comets show periodic flares every few hours, others remain eerily steady. Some grow erratic near perihelion, others fade quietly into the dark. The diversity suggests that the processes shaping comet activity are as varied as the systems they come from. In the case of Atlas and Borisov, the contrast could not be clearer. Atlas, restless and bright, flaring beyond predictions, may be the more volatile of the two. Borisov, quiet and restrained, may be more stable, or simply less responsive to the sun's heat, but both defy the traditional image of a blazing comet with a sweeping tail. Instead, they offer a subtler, quieter kind of light, a whisper rather than a shout. Perhaps this subtlety is what makes them interstellar. In the deep cold of space, comets evolve differently. Their surfaces may become insulated, their activity muted. Instead of dramatic eruptions, they release gas in faint, steady flows. Their light curves become smoother, less erratic, shaped by physics that is more deliberate than violent. In that sense, these interstellar comets may be teaching us a new definition of activity, one governed not by spectacle, but by endurance. Still, there is one thing that unites them all, from Oumuamua to Borisov to Atlas: unpredictability. No matter how carefully we model them, they always surprise us. A sudden brightening, a silent fade, an unexplained plateau, each deviation forces us to revise our assumptions. But that's the charm of comets, isn't it? They are, by nature, transient. They appear, change, and vanish, leaving us with nothing but traces of their passage in light. And perhaps, hidden in those traces, lies something larger, a statistical truth, a pattern in their apparent randomness. Because if we observe enough of them, we might start to see clustering, bursts of discovery in the same regions of the sky, alignments that hint at shared origins or sampling bias. That is where the study of brightness curves leads us next, not just into the life of individual comets, but into the broader question of distribution and probability. Why do we find them where we do? Are they truly linked, or are we simply looking more closely in some places than in others? That question, well, carries us naturally into the next horizon, the strange world of cosmic statistics, of chance and correlation, where patterns in discovery may reveal not alignment, but perception itself. When astronomers began to notice more and more faint wanderers appearing in the same corner of the sky, near Virgo, whispers of a pattern began to circulate. 2 interstellar visitors, 3, I, Atlas, and C 2025 V1 Borisov, seemed to align there, and for a brief moment, the human imagination leapt toward meaning. Was this mere coincidence, or could it be evidence of something larger? Perhaps a stream, a hidden river of interstellar material flowing past our solar system. The mind, ever hungry for order, seeks stories in noise, but science, you see, must wrestle with the delicate balance between chance and causality. It is here that the discipline of statistics becomes our compass. In the vastness of the sky, even randomness can look structured. The dome above us is not uniform in visibility or observation. Telescopes, limited by time, weather, and curiosity, tend to return to the same regions: the ecliptic, the galactic plane, those patches already rich with known objects. As a result, detections cluster where we look most, not necessarily where the universe offers more. This is the heart of what astronomers call observational bias. It is not deceit, but a kind of self-created illusion. We interpret the density of discovery as the density of reality, forgetting that our gaze itself shapes the map. If 2 interstellar bodies appear in the same field of view, one might be tempted to believe they belong to a shared stream, a galactic corridor of debris guided by ancient gravitational tides. But before such an interpretation can hold, we must consider probability. What are the odds, for instance, that 2 hyperbolic comets could appear within a few degrees of each other by chance alone? The answer depends not just on geometry, but on the limits of detection technology, the number of ongoing sky surveys, and the cadence of data collection. As the number of telescopes grows and their sensitivity improves, the rate of discovery naturally increases. Patterns that once looked extraordinary may dissolve into the ordinary when seen in the full light of statistics. Still, this concept sample bias extends deeper than where we look. It also concerns how we define what we see. To confirm an interstellar origin, we require precise astrometry over many nights. Only those objects that cross specific brightness thresholds and move fast enough to attract attention enter the catalogue. Countless fainter, slower bodies may slip unseen through the gaps. This creates another illusion, the sense that interstellar visitors prefer certain directions or velocities, when in truth, we may only be catching the brightest, most active few. The rest pass unnoticed, ghosts in the data. Imagine, for a moment, standing on a beach at night, watching meteors streak across the sky. Some seem to cluster, tracing paths that intersect. But that impression depends entirely on your perspective, your field of view, your patience. If you watched from another part of the world, at another hour, the pattern would change. In astronomy, we face the same paradox. What looks like the structure from one vantage point may vanish from another. That is why large-scale statistical models are essential. They allow us to remove the fingerprints of human habit and reveal what the cosmos truly intends to show. And yet, bias is stubborn. Consider how the most advanced sky surveys, Pan-STARRS, Atlas, Zwicky Transient Facility operate. Their scanning patterns favor certain declinations, avoiding the bright glare of the Milky Way's central band, where background confusion is greatest. As a result, the catalogue of discovered comets skews toward the quieter regions of the sky. When two interstellar objects happen to fall within those favored zones, we perceive a pattern where the instruments themselves have drawn the boundaries. The cosmos is not aligning, our algorithms are. The statistical correction for such effects involves a subtle dance of probability distributions. Astronomers simulate thousands of virtual skies, populating them with randomly oriented orbits, consistent with the known rate of interstellar visitors. Then, they run these simulations through the same detection pipeline used by real surveys. The result is a model of expected discovery bias. Only when the observed clustering significantly exceeds that expectation can we suspect something genuine, a physical association, rather than a perceptual one. So far, for 3I Atlas and C2025 V1 Borisov, the data do not breach that threshold. Their apparent nearness, though evocative, remains within the realm of chance. But perhaps this is where philosophy and science quietly meet. Humans evolved to see connections. Pattern recognition kept our ancestors alive. When the rustling of leaves coincided with the glimpse of a predator, the mind learned to link them. Now, that same instinct leads us to link comets across parsecs of space. The universe, however, does not share our storytelling impulse. It drifts, indifferent to the meaning we assign. And yet, paradoxically, it is precisely our urge to find order that drives science forward. For every illusion unmasked, another deeper order emerges. Take, for example, the history of interstellar meteor detections. A few years ago, two unusually fast meteoroids were recorded entering Earth's atmosphere. Their velocities suggested an origin beyond the solar system. At first, they seemed isolated events. Then, more such meteors were identified, enough to suggest a possible flux of interstellar material. Was that real, or merely the result of improved radar coverage and denser sensor networks? After statistical corrections, the supposed flux diminished, though it did not vanish entirely. The truth lay between. There was indeed an interstellar component, but our instruments had exaggerated its prominence. It's the same with comets. As our tools grow sharper, we must become more skeptical of our own enthusiasm. The more data we gather, the more likely we are to stumble upon coincidences. In a sky filled with billions of potential paths, even rare alignments will occur regularly. That's why probability is both humbling and essential. It teaches us that coincidence is not the enemy of meaning. It is the background against which meaning must prove itself. There is, however, a kind of poetry in statistics. Every discovery has its confidence interval, its margin of doubt, and within that uncertainty lies beauty. When we say, with 95% certainty, that two events are unrelated, we are also admitting a 5% whisper of possibility, that faint chance that nature has orchestrated something subtle. And so we keep watching, not to confirm our biases, but to let the data refine them into understanding. This tension between coincidence and correlation echoes through every branch of astronomy. In the 19th century, Observers believed the canals of Mars were evidence of civilization, an illusion born from the limits of their telescopes. Thought to be cosmic walls, until redshift surveys revealed their true distances. In each case, a pattern in data became a test of perception itself. We learned, painfully, that the universe's order often hides behind the veil of randomness, waiting for the patient and the cautious to see through it. You know, there's something almost existential in that. The sky is so vast that even genuine structure can look like noise until enough evidence accumulates. Galaxies form filaments, clusters, and voids grand architectures that once seemed impossible to discern. Perhaps, in time, we will find that interstellar visitors also trace such hidden patterns, streams shaped by long-forgotten gravitational tides, or the remnants of ancient stellar births. But until the statistics rise above randomness, we must hold that idea gently, like a hypothesis written in pencil. For now, the most responsible conclusion is restraint. The clustering of Borisov and Atlas may tell us more about ourselves, our instruments, our curiosity, our patterns of looking than about the universe itself. It is a reminder that discovery is not just about what we see, but how we see. Every dataset is a mirror, reflecting both the cosmos and the human gaze upon it. Still, acknowledging bias does not diminish wonder. In fact, it deepens it. To understand that even illusions have structure is to glimpse how knowledge evolves. Bias is not failure, it is the footprint of attention. It marks where our species has chosen to look, and therefore, where the universe has begun to reveal itself. The next step, naturally, is to disentangle these illusions from possibility, to imagine what scenarios could truly link objects like Atlas and Borisov beyond coincidence. Because once we have accounted for bias, what remains, however faint, may be the whisper of a real connection. And so, from the language of probability, we step once more into the realm of imagination and mechanics. If the alignment is not purely random, then what forces might create it? What if there truly exists a shared corridor of motion, a dynamic highway carved by the physics of stars? It is time, then, to explore those three grand possibilities: the accidental, the dynamic, and the ancestral, the great cosmic narratives that could explain why two wanderers appear to walk the same path across our November sky. When we finally peel back the layers of probability and bias, when we strip away coincidence and geometry, what remains is the question that keeps astronomers awake under long, cold skies. If not chance, then what? If 3I Atlas and C 2025 V1 Borisov truly share something more than the illusion of proximity, what could bind them? The answer, perhaps, lies in three great possibilities, three stories the universe might be telling through these wanderers. One is simple and humbling, that their alignment is random, a coincidence of projection. Another is grander, dynamic, that they travel along the same interstellar current, guided by invisible physics. And the third, most daring of all, is ancestral, that they once shared a birthplace, fragments of the same long-lost world cast out together into the dark. Each of these stories carries both beauty and burden, and only patient evidence will reveal which one truly belongs to the sky. Let us begin with the first, the accidental alignment, the idea that the two comets merely appear near each other from our perspective. It may sound unsatisfying, but in astronomy, chance is a more powerful sculptor than we often admit. The sky, after all, is vast, yet our line of sight compresses that depth into a flat dome. Objects separated by hundreds of millions of kilometers can seem to share a single point. It's like watching airplanes in a distant sky cross paths, though they fly at entirely different altitudes. The illusion is perfect, but the connection is false. In the same way, Atlas and Borisov may lie far apart in Atlas, real space, their orbits intersecting only in our imagination. And yet, the mind resists that answer. We long for structure, for design. To accept pure coincidence feels like surrendering to the randomness of the cosmos. But coincidence itself can be instructive. It tells us about probability, about density, about how often we should expect such alignments in the vastness of observation. If interstellar visitors pass through the inner solar system once every few years, and our survey coverage continues to widen, then overlapping trajectories will inevitably occur. What once seemed miraculous will become routine. So, if this is the true explanation, it carries a quiet reassurance that the universe is not teasing us, but reminding us of scale. Still, there's a poetic irony in that simplicity. Because even coincidences are meaningful in the way they provoke our curiosity. Every false alignment forces us to refine our models, to build better ways of separating projection from proximity. And in doing so, we prepare ourselves to recognize the moment when a real connection does appear. Science, after all, is built on the discipline of disappointment, the willingness to test even the most beautiful idea until it yields or survives. The second possibility reaches beyond coincidence. It imagines not two strangers crossing paths, but two travelers caught in the same current, a dynamic corridor of interstellar motion. This idea, sometimes called a galactic stream, suggests that the Milky Way may contain rivers of material dust, gas, and small bodies shaped by gravitational tides, supernova remnants, or ancient stellar associations. These currents move silently through the galaxy, unseen but not unmeasured, carrying with them the debris of countless worlds. If 3I Atlas and Borisov both belong to such a stream, their apparent alignment would not be random at all. It would be the local manifestation of a much larger flow. How could such a stream form? Imagine a star system billions of years ago, surrounded by a disk of icy debris much like our own Kuiper belt. Over time, gravitational interactions, perhaps a passing star, or the migration of giant planets, fling some of those icy bodies outward at escape velocity. Each becomes an interstellar traveler, carrying the chemical signature of its parent system. Now imagine not one, but many systems, all born in the same stellar nursery, ejecting material along similar trajectories. Those fragments would disperse over millennia, stretched and thinned by the galaxy's tides, yet retaining a faint coherence, a shared direction of motion, a common velocity frame. What we would see from Earth are scattered objects that seem unconnected, until, by chance, 2 or 3 happen to pass through our solar system at once. It's an alluring vision, isn't it? The idea that the space between stars is not empty but alive with motion, that we live, unknowingly, in the cross-currents of ancient worlds. In such a view, Atlas and Borisov are not anomalies, but emissaries, samples from the same invisible tide. If this is true, their velocities relative to the Sun should align not only in direction but in speed, their orbits tracing similar hyperbolic shapes through space. The proof, then, lies in astrometry, long, precise measurements of their paths before and after they pass near the Sunday. If their trajectories point back toward the same region of galactic longitude, the case for a shared current strengthens, but there is more to consider. If such streams exist, they would not only carry comets, they would carry dust, meteoroids, perhaps even fragments large enough to enter planetary atmospheres. The discovery of interstellar meteors entering Earth's skies may already hint at this. Some of these fast-moving objects, detected by radar and satellites, show velocities far exceeding the solar system's escape speed. Their directions cluster loosely around the same galactic coordinates as known interstellar comets. Could this be coincidence, or the faint trace of the same current passing through? If confirmed, it would suggest that interstellar material moves not chaotically, but in organized flows, like drifting leaves on a cosmic river. However, extraordinary claims require extraordinary caution. Galactic dynamics are complex. The Milky Way's gravitational field, stirred by spiral arms and dark matter, constantly reshapes trajectories. A stream coherent today may diffuse tomorrow. Over millions of years, only the most massive or magnetically influenced flows could persist. And yet, even if the structure is transient, the possibility remains that we are witnessing a momentary alignment within one of these ephemeral rivers, a glimpse of a galactic process, usually too vast to perceive. If this dynamic corridor hypothesis is correct, it would open a profound new window into cosmic history. Each interstellar visitor would become a particle of evidence, mapping the invisible architecture of galactic matter. By studying their composition, we could learn whether these currents are enriched in certain elements, whether they trace regions of past supernova activity or perhaps mark the boundaries of ancient star-forming clusters. The sky would cease to be random and become a kind of archaeology of motion. But then there is the third possibility, the most fragile and the most daring. That Atlas and Borisov are not merely fellow travelers, but kin. That they were once fragments of the same body, ejected together from their original system in a single violent event. It's an idea that treads the line between science and myth, and yet it's not impossible. In our own solar system, we know that collisions can split comets apart, sending sibling fragments on divergent paths that later cross again. Could such a thing occur across interstellar distances? Imagine a massive impact in a distant planetary system, perhaps triggered by the migration of a giant planet or the gravitational pull of a passing star. The collision shatters a large, icy body, flinging its pieces outward at slightly different speeds. Over eons, these fragments drift apart, separated by light years, but still moving through the same general corridor of space. If two of them happen to pass near the Sun within our lifetime, they would appear by cosmic chance to arrive together. Their alignment would not be a trick of perspective, but the echo of a shared origin. How could we ever confirm such a kinship? The answer, once again, lies in chemistry. If the spectra of Atlas and Borisov reveal identical ratios of volatile compounds, say, the same balance of carbon monoxide, carbon dioxide, and cyanide, it would suggest a shared environment of formation. More telling still would be isotopic signatures, identical ratios of deuterium to hydrogen or oxygen, 1:8 to oxygen, 1:6, numbers so specific that only a common birthplace could explain them. But obtaining such precision requires data of extraordinary quality, far beyond what our current instruments can easily provide. Still, there are other hints we might search for. Fragments born from the same progenitor might share peculiar physical traits, similar albedo, similar texture of dust grains, or comparable responses to sunlight-driven acceleration. Their light curves might reveal akin rotation patterns or synchronized non-gravitational effects. These subtle correspondences could form a circumstantial case for familial connection, even if direct chemical proof remains elusive. If this third scenario were true, it would be breathtaking. It would mean that we are witnessing not just interstellar travelers, but survivors of a single ancient catastrophe, a world long gone, still speaking to us through its fragments. Two pieces of the same frozen past, wandering for millions of years apart, only to cross paths briefly under our small blue sky. The odds are immense, but then, so is a universe's capacity for improbability. You see, these three possibilities, chance, current, kinship, are not merely scientific models. They are lenses through which we confront the nature of cosmic order itself. Are we living in a universe ruled by randomness, by fluid dynamics, or by memory? Each scenario tells a different story about what it means to exist in a galaxy where matter never truly stands still. Perhaps the truth lies in a combination. Maybe interstellar comets arrive randomly, but some belong to larger flows. Maybe within those flows are siblings, remnants of common origins. Nature, after all, rarely chooses between simplicity and complexity. It often contains both. What matters is how we test these ideas, how we transform wonder into method. And so, astronomers will keep measuring. They will refine the orbits, track the brightness, and chase every photon of spectral data. They will run simulations of galactic dynamics, model the long decay of comet families, and search for statistical fingerprints of shared motion. It is slow work, but slow work is the rhythm of truth. And perhaps, if we are lucky, the evidence will begin to tilt toward one of these stories. If we find more comets arriving from the same region of space, the idea of a galactic corridor will strengthen. If their compositions prove identical, kinship will rise from speculation to fact. And if neither occurs, then coincidence will stand vindicated not as failure, but as a quiet victory of clarity over illusion. Whatever the outcome, this triad of hypotheses forms the hinge on which the mystery turns. Beyond it lies the next question, even more ambitious. If a dynamic corridor truly exists, what shapes it? What invisible architecture carves such rivers through the interstellar medium? To answer that, we must look not at comets, but at the galaxy itself, the fields, the waves, and the forces that guide the motion of dust and ice across light years. And that, well, leads us gently into the next part of the journey, the search for the hidden rivers of the Milky Way, the unseen highways that carry these wanderers from one star to another, flowing endlessly through the dark sea of interstellar space. To picture a corridor in interstellar space, you must first unlearn the way we imagine emptiness. Space, we're told, is a vacuum, a silence so complete that nothing stirs, but that's only half the story. Between the stars, in the cold and the dark, lies a vast medium, diffuse but restless. It is not empty at all. It's filled with charged particles, magnetic fields, dust grains, and ripples from long-dead stars. The galaxy hums with invisible tides, and through those tides, small bodies drift, pulled and pushed, like seeds on a cosmic wind. These invisible pathways woven by gravity, sculpted by magnetism, stirred by ancient explosions, may be what we call interstellar corridors, or perhaps more poetically, rivers of motion. You see, when a star dies violently, it does not simply vanish. It erupts, sending shockwaves through the galactic medium. Those shockwaves travel for hundreds of light years, compressing gas, sweeping dust, and leaving behind shells of denser material. Over time, those shells fragment into filaments, curling under the galaxy's magnetic field. Matter tends to move along these filaments, following paths of least resistance. It's in these invisible channels that comets, dust grains, and rogue planets can flow drifting, sometimes for millions of years, until they encounter a system like ours. If you could map it all in light, you would see not chaos, but an immense network of streams, looping and crossing like the veins of a living organism. Perhaps 3I Atlas and C. 2025 V1 Borisov are passengers on one of these currents. Their trajectories, while seemingly random, could reflect a subtle inheritance from such structures. To us, they appear as solitary wanderers, but in truth, they may be fragments of a larger migration, the trailing ends of a filament still carrying the echoes of its creation. When we measure their velocities, we might find that they share the same galactic frame, moving together not because they know each other, but because the same ancient forces set them adrift in the same direction. The galaxy's magnetic field plays a quiet, commanding role here. Though unimaginably weak by human standards measured in microgauss, it stretches across thousands of light years, threading through gas and dust like invisible silk. Charged particles spiral along these lines, forming currents that can guide material across great distances. Even small icy bodies, electrically neutral but coated in charged dust, may feel a whisper of that magnetic influence. Over millions of years, that whisper becomes destiny. It bends their paths ever so slightly, steering them into alignment with the magnetic rivers that flow between the spiral arms. And those spiral arms, themselves, great luminous bands of star formation, are not static either. They move, slow waves of density rotating through the galactic disk. As they pass, they compress the interstellar medium, creating shock fronts that can act like gates or deflectors. Comets and debris caught near such boundaries might be nudged from one stream to another, or ejected entirely into the interarm regions, where gravity relaxes and drift dominates. From there, the long journey begins, a descent through the quiet spaces between stars, across tens of parsecs, until chance brings one within range of a new sun. If we could follow such an object backward, tracing its trajectory through the galaxy's gravitational and magnetic field models, we might one day reconstruct the river it once rode. Some researchers have already begun this kind of galactic cartography, using simulations of dust and gas dynamics to model how interstellar objects might move. What emerges from those simulations are not random scatterings, but coherent filaments, long, arcing flows that trace the same general directions as the galaxy's magnetic field lines. These filaments might explain why interstellar visitors appear to approach from similar parts of the sky. They are not siblings, but fellow travelers on the same invisible highway. The idea that our solar system is periodically swept by such currents is not new. Some models of comet influx suggest cyclical waves of activity, correlated with the solar system's oscillation through the galactic plane. Every 30 million years or so, we pass through regions of higher density, where the interstellar medium thickens and the gravitational landscape shifts. During these crossings, the outermost comets in the Oort cloud can be perturbed, sending cascades of icy bodies inward. It is conceivable that the same forces that jostle our native comets might also usher in visitors from beyond, foreign travelers drawn along magnetic corridors, caught briefly in the sun's gravity before continuing on. Now, imagine this in human terms, our tiny solar system drifting through an ocean of unseen flow, while around us, microscopic dust and ancient comets pass silently by. For every one that we detect, millions go unnoticed, but each carries a trace of where it has been. Atoms arranged by conditions in another star's cradle, isotopes imprinted by a different kind of light. When they enter our region of space, they cross invisible boundaries between stellar domains, blending histories. That blending, though imperceptible, is how the galaxy renews itself. It's a humbling thought that the same magnetic waves that once rippled from a supernova millions of years ago might still be steering comets toward our sun today. The blast of one dying star becomes the soft, persistent wind that delivers the relics of another. The galaxy, in this sense, is not just a collection of stars, it's a dynamic ecosystem, circulating matter, energy, and memory. We are part of its metabolism. Of course, verifying such cosmic corridors is no small task. To prove that two interstellar bodies share a common dynamic path, we would need to measure their full six-dimensional phase-space coordinates, 3 for position, 3 for velocity, with extraordinary precision. Then, by integrating those orbits backward through models of the galactic potential, we could see whether they converge. If they do, it would imply a shared flow, perhaps even a common origin region in the galaxy's structure. Such work requires not just ground-based observations, but coordination across space telescopes, astrometric missions like Gaia, and high-fidelity galactic simulations. It is science at the scale of the Milky Way itself. But beyond the technical challenge lies a deeper question. What would it mean if these corridors truly exist? If interstellar comets travel along rivers sculpted by magnetic fields and ancient explosions, then our understanding of cosmic connectivity would shift. No longer would interstellar visitors seem like random drifters. They would be the emissaries of structure, messengers of order emerging from what once seemed chaos. They would show us that even across billions of kilometers, matter moves not aimlessly but in rhythm with the galaxy's long pulse. And yet, perhaps it is that rhythm, the interplay between randomness and pattern, that makes the universe so hauntingly beautiful. Because these corridors are not roads in any human sense. They have no beginning or end, no fixed boundaries. They are gradients, probabilities, fluid architectures constantly reshaped by energy. What we call a stream is just a temporary alignment of motion, destined to dissolve and reform elsewhere. The universe is not carved in permanence, it is woven in motion. You know, sometimes I think of these magnetic filaments as memory lines, traces left by the galaxy's own thoughts. Each shockwave from a dying star becomes a 5-flea sentence written in dust and plasma, and the comets that drift along it are like punctuation, tiny markers of continuity. When we detect one, we are, in a sense, reading the galaxy's diary. It's just that the language is slow, and the pages are made of time. Perhaps this is what makes the alignment of Borisov and Atlas so evocative. Even if they are unconnected in origin, they remind us of how space itself connects everything. They are moments of intersection, evidence that paths do cross, that the cosmos is not as empty as it seems. Whether by coincidence or by current, they draw our gaze along the same invisible line, and for a moment, that line feels almost deliberate. But we are not done yet. For to map these interstellar rivers, to test whether such corridors truly exist, we must turn to the tools of our era, the instruments capable of tracing faint motion across years, of reading the spectra of dust and gas carried between stars. The next step, naturally, leads us from theory to practice, from imagining the rivers to learning how to chart them. And that, I suppose, brings us to the next question in this long unfolding story. How do we build the eyes and instruments that can follow these travelers through the vast and shifting sea of interstellar space? To map those invisible rivers of matter we imagined, we must build the tools capable of seeing them not in light alone, but in motion, in chemistry, in the faintest tremor of gravity itself. The great paradox of 2025 is that while our telescopes can now resolve galaxies billions of light years away, the nearby wanderers, the small interstellar messengers drifting through our cosmic neighborhood, remain elusive. Their light is weak, their motion subtle, their presence fleeting. To catch them, we need more than just bigger mirrors. We need a choreography of precision, a network of instruments and minds synchronized across the world and beyond it. The first instrument in this symphony is astrometry, the art of measuring position. It sounds simple. Find a point of light, record where it is, but in truth, it is a dance against uncertainty. When astronomers say they have measured a comet's position, they mean they have captured photons that have traveled millions of kilometers, distorted by Earth's atmosphere, bent by optics, and delayed by time. To extract truth from that chaos, they compare the comet's location against reference stars, catalogued to micro-arcsecond precision by missions like Gaia. Every observation adds a thread, and with enough threads, the orbit begins to emerge. For interstellar objects, astrometry must be relentless, night after night, tracking their slow drift against the stars to tease out the curvature of their path. Only with long, continuous observation can we distinguish a parabolic intruder from a true hyperbolic voyager. Then there is spectroscopy, the fingerprint of light. If astrometry tells us where an object is, spectroscopy tells us what it is made of. Each atom, each molecule, leaves a signature in the spectrum, a barcode of emission or absorption lines. For comets like Borisov and Atlas, wideband spectroscopy can reveal the gases escaping from their surfaces: carbon monoxide, cyanide, methanol, water vapor. These ratios tell us about their origins, their temperature of formation, and whether their chemistry aligns with known solar system comets or diverges into the truly alien. High-resolution spectrographs mounted on telescopes such as Keck, VLT, and Subaru are capable of detecting these spectral lines even when the light is faint, provided the observation is carefully timed around perihelion when activity peaks. But spectroscopy is not only about composition, it is about motion too. Each spectral line shifts slightly, according to the Doppler effect, revealing the velocity of gas jets or the comet's rotation. With multiple epochs of data, astronomers can build three-dimensional maps of the outflow, tracking how it evolves with solar heating. It's as though we could feel the breath of the comet itself, pulse by pulse. Beyond the professional observatories, there exists another, quieter network. The world of amateur astronomers and semi-professional skywatchers who, armed with modest telescopes and dedication, contribute vital data. Their role is far greater than most realize. Because they can observe nightly, they provide the temporal continuity that large observatories cannot. Many of the early detections of faint tails, subtle outbursts, or unusual brightening come from this distributed human network. Their images, when properly calibrated, can feed into global databases, adding density to the light curves and astrometric chains. However, to make all this data meaningful, there must be standardization. In the past, each observer processed images differently, subtracting backgrounds, stacking exposures, and stretching contrasts according to personal technique. The result was beautiful but inconsistent. Now, under coordinated projects like the International Comet Observation Network, efforts are being made to unify these methods. Observers are trained to stack images along the comet's motion vector rather than the star field, to preserve the integrity of the coma and tail, and to use consistent photometric filters that allow direct comparison between datasets. This might sound technical, but it is the quiet scaffolding on which scientific reliability rests. And then there's the data pipeline itself, the invisible infrastructure that carries raw images from mountaintop telescopes to processing centers. Each frame must be calibrated with dark and flat fields, corrected for distortion, time-stamped to atomic precision, and cross-referenced against catalogues of stars. In this way, millions of photons, each captured as digital counts, become part of a coherent global record. Increasingly, this work is aided by machine learning systems trained to detect faint moving targets automatically, These algorithms can scan the sky faster than any human, identifying potential comets or asteroids in near real time. But they, too, must be watched carefully. Automation accelerates discovery, but it can also amplify error. False positives masquerade as new worlds, unless human eyes intervene to confirm. Astrometry and spectroscopy may be the pillars, but imaging, the art of seeing in shape and structure, remains the soul of observation. High-resolution imaging allows us to study the morphology of the coma, to identify jets, fans, or asymmetries that reveal the comet's internal geography. Spacecraft like the Chinese Tianwen and future missions from NASA and ESA have begun experimenting with adaptive optics and deep-field imaging of interstellar objects, though the challenges are immense. These targets move quickly against the stars, requiring telescopes to track at unusual rates. Their surfaces are dim, often below the threshold of complex contrast where detail emerges. Still, each image, even blurred, carries hints of geometry, a faint crescent revealing directionality, a brightness gradient marking the nucleus's rotation axis. In the coming years, the Vera C. Rubin Observatory will transform this landscape. Its wide-field telescope, scanning the entire southern sky every few nights, will generate petabytes of data, detecting transient phenomena from supernovae to faint interstellar visitors. For the first time, we may have a near-continuous visual record of every moving object brighter than magnitude 24. That means not only faster discovery, but richer context, knowing what came before and after each event, seeing how brightness evolves even before an official detection. The Rubin data pipeline, combined with astrometric catalogues from Gaia, will form the most detailed dynamic map of the solar system ever built, extending seamlessly into the interstellar frontier. Still, observation is only half of the endeavor. The data must be interpreted, modeled, simulated. Dynamicists use the positions and velocities collected by observers to integrate backward in time, testing whether the object's path can be traced to the galactic frame. Chemists use spectral data to infer volatility and molecular structure, reconstructing the environment of formation. Statisticians use the ensemble of detections to model population distributions, searching for the hidden biases that shape what we find. It's a chain of effort stretching from the mountaintop to the mainframe, each link dependent on the other. And then, perhaps most beautifully, there's the collaborative spirit that underpins it all. The study of interstellar comets is not bound by borders or hierarchies. A small observatory in Namibia can complement a university telescope in Chile, both feeding into a shared repository, accessible to anyone with curiosity and skill. Data democratization, once a fragile dream, is becoming reality. Public archives like the Minor Planet Center, NASA's Planetary Data System, and the European Space Agency's repositories ensure that discoveries do not vanish into proprietary vaults. This transparency allows replication, verification, and the quiet joy of independent discovery. In many ways, the process mirrors the very phenomenon it seeks to study. Just as interstellar objects drift through gravitational networks, exchanging energy as they pass, so too does scientific knowledge flow through networks of people and machines. Ideas migrate, collide, merge, and evolve, carried by the invisible currents of curiosity. That is the true beauty of modern astronomy. It is not just the observation of connection, but the enactment of it. Yet, for all our sophistication, we remain bound by light and time. No telescope can yet follow a faint comet beyond a certain distance. No spectrograph can catch every molecule before it disperses. We are always a step behind the traveler. By the time the instruments lock on, the object has already begun to fade. That limitation shapes strategy. We must anticipate, not merely react. Predictive algorithms now use early motion data to forecast where an interstellar object will be weeks ahead, allowing coordinated campaigns of observation. Space-based telescopes like the James Webb, which can observe in infrared, are cued in advance to catch the brief window when the object is both bright and active. It's a choreography of timing, requiring global cooperation. And as technology advances, the frontier moves closer. In the near future, dedicated missions may be launched specifically to intercept these interstellar visitors. Concepts like ESA's Comet Interceptor or NASA's planned near-Earth object missions could, with the right trajectory, be repurposed to rendezvous with a passing interstellar object. To do so would be to capture the first direct sample of material from another star system, a scientific leap akin to the first landing on the Moon. But even before such missions fly, the groundwork is being laid now, in the calibration of telescopes, in the alignment of datasets, in the patience of observers who sit under the stars and record another faint dot in Virgo. All of these tools, together, form the sensory apparatus of humanity, the collective eye turned outward. And perhaps, when we think of these instruments, we should not imagine machines alone but the minds that interpret them. Each dataset, no matter how technical, begins as a moment of wonder, a decision by someone, somewhere, to look a little longer. That act of attention is the seed of all discovery. It is fitting, then, that this chapter of the story ends not with the instruments themselves, but with what they promise. Because if these tools succeed, if the astrometry sharpens, if the spectroscopy deepens, if the collaboration endures, we will soon face the question not just of observation, but of understanding. What would it mean if the evidence points toward a true interstellar corridor, a real river of matter threading past our sun? How would that change our picture of planetary formation, of galactic ecology, of our place within it? And that, well, is the threshold we are now approaching, the moment when observation becomes revelation. From the quiet hum of data will rise a clearer image of how these visitors move, how they are born, and what they carry. The next step, naturally, is to ask the great if. What if the corridor is real? What would such a discovery demand of our models, our imagination, and our sense of belonging in the Milky Way?